So this is based on some work that appeared recently with Simon Maronford, Amit Sever, and Sasha Riguedo. So let me give some brief introduction and then present the results without much detail, and you can refer to the paper if you are interested in more details. So we were interested in considering theories of massive particles, which are characterized by their mass and by their spin. So we would also like to assume that these particles interact very weakly and they're approximately stable. So this is some class of theories, and the idea is that this class of theories is kind of similar to what we observe in nature in quantum thermodynamics, where we have many resonances, and they can be, in some approximation, viewed as weakly coupled particles of some spin. Now, there are many examples of such theories where these statements are rigorous. That we have many particles with some spin, and they're approximately stable. So, for example, if you consider tree-level string theory in flat space, then we have many, many resonances that populate all the possible spins up to infinity. And there are large degeneracies and also Hagedorn densities of states of particles, as we know. Another interesting example, which is the primary example that I'll be interested in, is Yang-Mills theory, as Argent plus perhaps matter. So as long as these theories confine what we expect based on experience, Monte Carlo simulations, and let's say gauge gravity duality, is that there will be resonances with any possible spin, and there will be a Hagedorn density of states, but we don't expect quite the same amount of degeneracies as we observe in string theory. Another example that fits this class of theories that I've just defined is just classical field theory. So if you take, for example, phi cube theory in, let's say, 4 dimensions, it describes a spin zero particle which is weakly interacting if the coupling constant lambda here is small. So there are these classes of theories that are within these assumptions, and we would like to see what we can say about it. In particular, can we say something new about Argand Yang-Mills theory? Now, historically, of course, Yang-Mills, the resonances of Yang-Mills theory was left to string theory, and then string theory was reconnected with Yang-Mills theory by the ideas of holography. But here, the main question that I would like to pose is whether there is a precise limit of string theory in flat space that is connected with Yang-Mills theory. So is string theory in flat space, which is what has been discovered in the 60s as a result of investigating these resonances that appear implicitly, is this theory connected to Yang-Mills theory in flat space in some precise limit? So that's the question that we would like to discuss. So the main tool that I'm going to use is the S matrix. The S matrix, or more precisely the scattering amplitude, is a function of two complex variables, S and T. And this S and T can be viewed as the energy in the center of mass and the scattering angle if you're thinking about S channel scattering. So S is just the square of the center of mass energy. And the variable T can be just viewed as the angle of scattering through these formulas. So this scattering amplitude, A, which is a function of two complex variables, obeys very interesting general constraints that are not so easily mutually satisfied. So the first constraint that follows from general principles and the assumption that we have some particles and some spins that are exactly stable in some limit is that when we tune the external energy in the center of mass to be exactly on one of the resonances, then the amplitude must look like must have a single pole in that variable, but in the other variable, T, it must be a sum of polynomials of the Legendre type with positive coefficients. So these coefficients have to be importantly strictly positive.
Sure. Take this one. Okay.
Another constraint is that the amplitude has to be invariant under exchanging S and T. That is just channel duality. So these are some general properties that these objects must obey, in the limit that the resonances are exactly stable. But these conditions by themselves are not so interesting, because there are many, many solutions, and many of the solutions are not really interesting to us. For example, if you consider this tree-level phi cube theory that I've introduced in the beginning, then if the coupling lambda is very small, then this resonance would be stable, and the scattering amplitude would be just the sum of two simple poles in the s variable and in the t variable. And so this solves all the constraints that I have imposed before. It's invariant under the exchange of S and T, and it has polynomial residues when you focus your external parameter S to be at the resonance. So this is not an interesting example. However, there is a very effective way of eliminating all of these classical filters which we're not really interested in. And this comes through the following additional condition we would like to impose. This condition is very interesting because it automatically eliminates all the uninteresting examples. So we call this condition the boundedness condition, which just says that when you take the parameter S to be very large and you multiply the amplitude by an appropriate power of S, which is given by S to the minus J naught, where J naught is some spin that exists in the spectrum. So if there is a t for which this thing goes to 0 when S goes to infinity, then we would say that the amplitude is properly bounded. And now what I would like to explain is that in Yang-Mills theory and string theory, this condition is satisfied. However, it eliminates all the classical filters from consideration. So importantly, J naught has to be a spin of a particle that exists in the spectrum, and P naught has to be some parameter. So this boundedness condition is satisfied in Yang-Mills theory. And more generally, it is satisfied in any theory which has a UV completion and also resonances with spin higher than 2. This follows from these arguments in this paper. So because in Yang-Mills theory we believe that there are resonances with any spin up to infinity, and because Yang-Mills theory has a UV completion, it follows that this condition is satisfied in Yang-Mills theory. In fact, it can also be shown to be satisfied in Yang-Mills theory by direct computations in the asymptotically free regime. So this boundedness condition is satisfied in Yang-Mills theory. It's also clearly satisfied in string theory, as I will explain again soon. And once this condition is imposed, the amplitude can be essentially written as a sum over S channels poles only. So now we have an expression for the amplitude, which is a sum over infinitely many resonances, which contribute these poles in the S channel, but the dependence on T is through these polynomials in the numerator. But now this duality is highly non-trivial, because T appears only in the numerator and S appears in the denominator. So now duality is non-trivial, but this sum converges in some domain of the complex variables T and S. So the fact that you can write the amplitude using only S channel resonances follows from this boundedness condition, which is upheld in Yang-Mills theory and string theory and some other examples, but it's not true in classical field theory. So you can view this equation that A of S and T should be equal to A of T and S as some sort of bootstrap equation. So the S channel resonances have to reproduce the T channel resonances because the T channel resonances are highly non-obvious in this formulation. So it's immediately clear that any such theory that obeys these conditions that I've imposed, namely unitarity, boundedness, and duality, any such theory must have infinitely many particles. Because if you don't have infinitely many particles, you could never reproduce any poles in the T channel using the expression that I wrote. Also, such theories must have particles of unbounded spin, because otherwise the dependence on T is essentially a polynomial. And you cannot reproduce any pole in T in that way. So such theories I'm going to refer to such theories as massive higher spin theories. So this is some class of quantum field theories that we would like to investigate. These are theories of many, many particles with various spins, and they interact very weakly and they're approximately stable. And we're going to refer to them as massive higher spin theories. So there are many interesting questions that you can ask about massive higher spin theories. Perhaps the first question that you can ask is what are the particles that have the highest spin with some mass? So this question can be answered by considering the Regge limit of this amplitude A, which is a function of S and T. So the Regge limit is characterized by sending S to infinity while keeping T fixed. And in that way we get some function of T times some power of S. And this power of s is given by some function j of t, which is satisfies the following property. When j of t n is an integer, a positive integer, then we have a particle with spin n at energy with mass squared Tn, and therefore this dependence on s here becomes a polynomial, and this is characteristic of a particle of spin n. So, so to summarize, there is some function j of t that is defined through that limit mathematically, and when this function satisfies this equation, then we have particles that spin very fast. In fact, the solutions to this equation define the leading radius trajectory of the theory. The leading radius trajectory is just a bunch of particles that rotate, that have the highest spin given some mass. So if we could imagine a Gedanken experiment where we perform small angle scattering, we could measure this function j of t at negative t, because the angle of scattering is real when t is negative. However, to solve this equation, you need to imagine doing scattering maybe at imaginary angle, and we'll discuss that much more. So, from phonological considerations and many other indirect considerations, in confining gauge theories, the function j of t should look like that. So, the solutions to the equation j of t equals n, where n is a positive integer, would occur at positive values of t, which are not the physical values which we measure which we use when we do physical scattering experiments, but nevertheless they are completely well defined. So this is what we find in confining gauge theories, and in string theory, in flat space, famously, we get exactly linear trajectories. So j of t is exactly linear in string theory, while in confining gauge theories it should curve by because of asymptotic freedom. So we see that for negative t, which is for negative t, Young-Mills theory and string theory are not in good agreement. So the Veneziana amplitude, which describes free string theory in flat space, is not in good agreement with Young-Mills theory for negative t, because it does not capture, of course, asymptotic freedom. But on the other hand, we see that for positive t, the two plots are very, very similar, because they both look asymptotically linear. So what I'm going to prove is the following thing. What I'm going to prove is that any massive higher spin theory, which is the thing that I defined, behaves like this expression for a large positive S and T. So this regime does not correspond to physical angle scattering. It corresponds to scattering at high energies at imaginary angles. However, this is still something that has lots of implications that I'm going to explain now. So even though it does not correspond to physical scattering, it has implications which are still very interesting for both phenomenology and theory. And I'm going to explain the implications of this assertion now. So, of course, it's true that this is the right limit at large S and T for free string theory. This is just some analytic continuation of the Gross-Mendel formula. But we also claim that this must be true in any massive higher spin theory, in particular in Young-Mills theory. What are the implications of this claim? First of all, it implies that there must be infinitely many asymptotically linear and parallel trajectories. So the claim is that one can prove that there must be asymptotically linear radial trajectories in large N Young-Mills theory. Furthermore, if you take that expression that I wrote on the previous slide and you transform it to improper parameter space, you find that even at very large energies and at very large impact parameters, there is a non-trivial inelastic component to the amplitude. So that follows just from the expression that I wrote on the previous slide. However, there is some one has to do it carefully. But in any case, this expression for the inelastic part of the amplitude at large impact parameter and at high energies implies that the theory must contain strings or some sort of flux tubes. Because there is this logarithm of the energy in the denominator, which is typical for strings, which have fluctuations in the transverse directions that go like the logarithm of the energy. So therefore, to summarize, before I plunge into the details, we claim to be able to prove that any weakly coupled theory that has any resonance with spin higher than 2 must contain strings. It must have infinitely many asymptotically parallel radial trajectories, and it must agree with flat space string theory in this fixed imaginary angle, high energy regime. So that's the claim. And now I'm going to briefly explain what are the methods that are used to establish this claim. The methods are also quite interesting, and they have some new ideas. So we're going to use this property of Legendre polynomials that the positive, for x is bigger than 1, the Legendre polynomials are positive, which has the following implication for us. When we tune the external energy to be at a resonance, then as I explained in the beginning, we have some numerator, which is a positive sum of Legendre polynomials divided by a pole. However, because of this property that the Legendre polynomials are positive in some regime, it follows that when p is positive, namely when the scattering angle becomes imaginary, all the residues are actually positive. So the numerators in this expression are all manifestly positive because the coefficients are positive and the polynomials are positive. And so one is led to the following interesting conclusion. As a function of s, we see that we have an object which has poles, but all the residues are positive. And therefore there must be at least one zero between every two poles. In addition, there may be zeros of the scattering amplitude which are not between two poles, and those we will call excess zeros. And the first interesting question is, how many zeros have we got, in addition to the zeros that must occur between two adjacent poles? So to determine the number of zeros, we sort of allude to a generalization of what's called the Levinson theory of quantum mechanics, but it's actually very easy to prove in this context. So we consider the scattering amplitude, the logarithm of the scattering amplitude, which in the Regge regime is j of t times log of s. And now j of t log of s has a discontinuity in the s variable as you cross the real axis, the negative real axis. And this discontinuity must come from the sum over the poles of the amplitude minus the zeros of the amplitude. Because every zero contributes a positive every zero contributes plus 1 to the discontinuity of the logarithm of the amplitude, and any pole contributes minus 1 to the discontinuity of the logarithm of the amplitude. So therefore, we actually know how many more zeros we've got compared to poles in the amplitude. It's exactly the number of high spinning resonances. So that's a nice sum rule that relates high spinning resonances or fast spinning resonances to the number of zeros of the scattering amplitude. Let me try to explain it in a picture. So for some generic positive t, the amplitude has many, many poles. These are denoted by these red squares. Because of this unitarity argument that I've given before, between every two poles there must be a zero. Now the idea is that when you increase t, j of t also increases, because that counts how many fast spinning resonances there are. So when we increase t, the zeros just move to the left. So we just imagine that there is a flux of zeros going to the left. And when you hit the resonance, they exactly coincide with the poles, because the amplitude needs to be a polynomial at that point. And then they continue past the poles, and they join the excess zeros. So once you crank up t, the number of zeros has increased here from 7 to 8. Because now there is this additional zero that came from the right. So therefore, the picture is that the amplitude has many zeros, many poles, but the number of zeros is bigger than the number of poles, and the zeros keep piling up as we increase t. So therefore, when t is very, very large, the amplitude is essentially dominated by the zeros. The excess zeros. The zeros between poles here don't really matter. So those zeros that are between poles, which we call unitarity zeros, don't really matter in the asymptotic regime of high energies and very large imaginary angles. The only thing that matters in that regime are these excess zeros. They dominate the amplitude. So therefore we can write an expression for the amplitude, which is for the logarithm of the amplitude, using the density of zeros. So if we knew exactly where each zero is for every given t, we could have reproduced the amplitude in that regime from this convolution of the density against the logarithm of z minus s. Now, also, we can, since t and s are imagined to be extremely large compared to any threshold scale in the problem, we can use dimensional analysis and simplify the density of zeros into that form. So we can think about it. We can think about it as a problem in electrostatics. So we have some density, which we can view as the density of some positive charges. And this logarithm can be thought of as just the electric potential due to a charge in 2 dimensions. And this is some prefactor, which is not really important. So the idea is that the logarithm of the amplitude can be viewed as coming from the distribution of some positive charges in 2 dimensions. We can similarly take some derivatives of this amplitude and get something that looks more like the electric field of the corresponding distribution of zeros. So that's obtained by taking a derivative of the logarithm of the amplitude. We get an expression that looks like the electric field of the same distribution. Now, unitarity and crossing are not completely, so crossing is highly non-obvious in this formulation, and unitarity is slightly non-obvious. Unitarity imposes that this density of zeros has to be positive definite, but it actually has more implications. So what I'm going to discuss now is the first implication of unitarity, and then I'll discuss the implications of crossing symmetry, and then I'll conclude. So the first implication of unitarity is a trivial property of sums of polynomials with positive coefficients. You can take the second derivative, you can see that it's positive. So I'm not going to explain the details, of course, but this immediately leads to the conclusion that the dipole moment of the distribution of zeros, it must be bigger than a half. So the distribution of zeros must be skewed to the left, which is in agreement with this picture that I had before. You see that most of these excess zeros must lie to the left. In fact, you can bound the dipole moment to be more than a half. So more than a half of them have to be to the left, in some sense. This is satisfied for the Veneziano amplitude, in which the density of zeros is just a uniform distribution along the negative imaginary axis, going from 0 to -1. And for the Veneziano amplitude, this bound is saturated. So the dipole moment is exactly a half. There are also extremely non-trivial constraints that come from crossing symmetry. So if we take beta, which is S over T, to be very large, so this is the Regge regime in the F channel, then we have something that looks like a multiple expansion from electrostatics, using this language of density of zeros. But crossing symmetry tells you that you can also now study the small beta expansion, because that looks like the Regge regime in the P channel. So one can write an analogous expression for how the electric field is going to look like at small beta. But the positivity of that second derivative that I explained before implies that k is bigger than a half. Where, let me remind the definition of k. For the sake of this argument, I'm imagining that the Regge trajectories are t to the k, and k is to be determined. So the idea here is that, just for the simplicity of the presentation, I'm going to try to prove that k is equal to 1, that asymptotically the trajectories must be linear, and therefore k must be 1. So we see that already from the simple considerations, one arrives at the conclusion that k must be bigger than a half. So in any consistent theory of massive higher spins, the trajectories must rise faster than the square root. This is a highly non-obvious conclusion that in fact is not respected in some examples that were constructed in the past. Furthermore, from this expression for the electric field at small beta, it immediately follows that k must be smaller or equal to 1. So we've already bounded k between a half and 1 with very little work. This bound follows just from the fact that since the dipole moment is bigger than a half, the electric field cannot vanish at some point. So it's a simple argument of that sort. Now there is a more, slightly more elaborate condition that follows from unitarity that imposes further restrictions on this distribution of zeros and selects k equals 1 as the only remaining possible solution. So one has to study more carefully what would be the properties of zeros of positive sums of Legendre polynomials. So analogous problems have been studied for quite a time in the mathematical literature, and we just borrowed some results. So it turns out that if you look at positive sums of Legendre polynomials, and if the coefficients don't decay fast enough, if the coefficients don't decay too fast, then it turns out that all the zeros condense within the unit circle. So the unit circle is much, much bigger. This is some region, a small part of the unit circle. And this is something that can be established rather rigorously, and we tested it extensively. So when you have like a high rank polynomial with positive coefficients, the zeros just form some well-defined distributions, and this is an example. Using that condition that all the charges are within the unit circle, as follows from those considerations, it's actually crossing imposes much more severe constraints. So for example, if we assume that the distribution of zeros is within the unit circle, and if we impose crossing symmetry, then this problem in electrostatics has a unique solution. It's not so easy to write an electric field that comes from a distribution within the unit circle that is also invariant under crossing. Since crossing takes beta to the power -1 in this case, we found that there is a unique solution, which is given by a hypergeometric function, for the electric field outside of the charge distribution. Now, that electric field has some moments which are inconsistent with the previous bounds unless k is equal to 1. So the combination of all these arguments and the inequalities finally leads to the conclusion that asymptotically the only consistent solution is that the Regge trajectories would be linear. In fact, one can show that it's exactly the Veneziano form that one finds in this limit. So in the case that k is equal to 1, that hypergeometric function collapses to a logarithm, and the logarithm can be shown to be exactly the same expression that you are familiar with from string theory. So we see that even in Yang-Mills theory, one can determine the scattering amplitude in this fixed imaginary angle energy regime to be that form. And this has some implications for Regge trajectories, the density, the degeneracies, the density of particles, and also for the existence of strings. So one can say that one can establish the existence of strings in Yang-Mills theory. Let me just make some concluding comments. So the S-matrix bootstrap program, that is what the S-matrix bootstrap program, which is what we've been discussing now, seems to still have potential to lead to interesting new results. Of course, we're using a lot of hindsight. We're using recent results from the lattice, calculations in great gravity duality, which suggested in which region one should look, and also some effective string theories, which also have been pretty powerful in teaching us important things about Regge trajectories. So it's therefore not surprising that this kind of bootstrap analysis wasn't done 4 or 5 decades ago. And now it can be done, and it leads to rather interesting and powerful results. Of course, one can assume that in the future it will be possible to improve this analysis and study more precisely how degeneracies between particles and Regge trajectories are lifted in Yang-Mills theory, how linearity is avoided. I mean, exact linearity cannot continue forever, so one has to find some corrections. And then there are various other formal questions about the relation to conformal field theories via the Mellin transform, the uniqueness of Veneziano, if you assume that the trajectories were exactly linear. And also, one thing that follows rather directly from this analysis is that Yang-Mills theory and string theory are actually only separated by a phase transition in the variable t, because we see that at large positive p, Yang-Mills theory and string theory are the same. However, at negative t, which is the physical small angle scattering regime, they must be different. And one can argue that, at least analytically, this is something like a Stokes phenomenon. So it would be nice to characterize this, let's say, phase transition or Stokes phenomenon that relates Yang-Mills theory and the asymptotically free regime. Well, thanks so much, but before I conclude, I wanted to mention that the Strings Conference next year will be in Tel Aviv, so you're all invited to come. And here's the website, the tentative website that we set up for the conference. Thanks so much.
So we have time for some questions.
Did you make any assumptions about the dimension of space-time, or did you allow it to vary?
For this analysis, we've only assumed that the number of dimensions is bigger than 2. Because in 2 dimensions there is only one kinematical variable, and the analysis would be very different. But for this analysis, we basically let the dimension be free.
And there was no problem with going to high dimension?
So if you look at the Veneziano, we're only claiming that string theory in flat space is identical with these massive higher string theories at large S and P, and when they're both positive. Actually, in that regime, you don't see immediate violations of unitarity, even if the number of dimensions exceeds 1/6. So there's no contradiction. But there may also not be interesting massive higher string theories about, let's say, 4 or 5 dimensions.
More questions?
I mean, in the last part of the talk, you claimed that Yang-Mills and string theory are separated by phase transition.
Yes.
What is the meaning of this phase transition?
Yeah, okay, I can explain that. I've actually explained a very small fraction of what I intended to explain. But I can explain that a little bit better. So when we define the Regge limit, we take something fixed, and then we take S to be very large. And then we read out the function g of t from this expression. So this is starting from some meromorphic function with two variables, and you take some asymptotic limit. What I'm discussing is how this function g of t looks like a positive large t. And then I've analytically continued that asymptotic form to the whole complex length. But analytically continued the asymptotic form may not commute with the asymptotic form of the analytic continuation of the amplitude itself. So what I can show is that while it's true that here it's asymptotically linear, it cannot be asymptotically linear here. And you can show that there must be some kind of Stokes line in between, or phase transition. So what I'm saying is that analytic continuation and asymptotic limits necessarily do not commute in Yang-Mills theory. It's necessary. You can even make a stronger claim. You can prove that any amplitude which does not have a Stokes line must have exactly linear trajectories. So it follows that in Yang-Mills theory there must be some sort of phase transition. So the asymptotic continuation is the asymptotic limit at positive t, when analytically continued, cannot describe the asymptotic limit of the true amplitude at negative t.
More questions?
Thank you. Did you mention that you can predict the infinite number of velocity trajectories?
Yes.
How to see that?
I haven't quite explained it. So the only thing that I sort of explained is that you can prove that asymptotically g of t must be linear. This is the only consistent solution that we found. If you assume that g of t equals t to the power k or something, the only solution that is mathematically allowed is k of 1. So from this it doesn't yet follow that there are infinitely many trajectories. But we also have a pretty precise determination of this function f of t. And whereas we've been also able to predict the asymptotic expressions for various partial waves. So there are these coefficients here, the f and j squared. So we've been able to compute them at large t and s in some saddle point approximation. And from that it's clear that one trajectory is not enough. More conceptually, if you assume that your amplitude obeys crossing symmetry, one Regge trajectory in the S channel would never produce Regge behavior in the P channel. And crossing symmetry is built in to the formalism that we're using. So you must have, it's sort of intuitively plausible. There must be infinitely many Regge trajectories, because you could never produce Regge behavior in the dual channel if you just had one Regge trajectory. But this can be mathematically shown. I haven't explained it.
So one final question. Please wait for one.
So I may not be understanding everything, but it seems like a very interesting connection between the tree-level string amplitudes and something non-perturbative in the gauge theory.
Correct.
So the full string theory, if you were to include everything, of course we don't always have a full completion of it, but this S matrix would include gravitational physics like black hole formation and evaporation and all sorts of things that are very different from what you get in the full gauge theory. So how should I think about the way you're interpolating from one theory just the tree level, the other theory?
Yes. I think that perhaps historically the reason that Veneziano was dismissed as a not good model for QCD, partly because the low-line resonances are very different. However, here I'm not claiming anything about the low-line resonances. I'm just claiming that in any consistent Yang-Mills theory at large n, which confines, at large S and T, which are positive, this has to be the asymptotic form. Now, this asymptotic form is sort of oblivious to the fact that there is a massless graviton or a tachyon. This is just the asymptotic form. It's clearly informed in the regime of the Veneziano amplitude, or the analytic continuation of the Gross-Mender regime, if you want. But that's the claim. We claim this is true in large and Yang-Mills theory.
Okay, one more question.
As long as n is much, much larger than s.
Exactly. Indeed.
Which, of course, is extremely emphasis.
Completely agree. S and T have to be large compared to the QCD scale, lambda QCD squared, but they cannot exceed n parametrically, or otherwise the resonances would not be stable anymore. So this is a well-defined parametric regime. in which this formula is supposed to be true.
I guess these results can also be obtained by thinking about the flux tube picture. And so could you comment on this?
Yeah, so we were trying to derive the flux tube picture. So, and to some extent we can derive the flux tube picture, to derive the fact that there must be strings in Yang-Mills. Now, you're asking what has been achieved with flux tube, so I can summarize in maybe a few sentences. So if you assume that there is a flux tube in Yang-Mills theory, then it follows that the linear trajectory is linear. However, there have been some problems computing the sublinear corrections. So it's still an open problem to compute the next correction to the linear. This has to do with some dynamical clasps that develop on the rotating flux tube. About this, I actually don't know. So I do not know if this asymptotic limit at large and positive SNT can be derived from the flux tube picture. But I believe it can.
Okay, I think in view of time we should relegate further questions to Zohar for the lunch break. And let's thank Zohar and all the speakers of this morning.